Uh, my presentation concerns a stability of KdV Solitons with respect to transverse perturbations. The results we obtained together with my co-authors from Nizhny Novgorod, Professors Petruchin and Pelinovsky. This is the content of my talk. No, and as you probably know, KdV equation was derived very long ago to describe nonlinear waves on water surface. These authors also obtained the solution in the form of solitary wave or soliton. However, this result was practically forgotten for many years until in 60s of the last century, it turned out that KdV equation describes many wave modes in plasma physics. Kadamtsov and Petviashvili decided to study the stability of solitons with respect to transverse perturbations. And they derived, to do this, they derived the famous Kadamtsov-Petviashvili equation. They showed that solitons are stable if dispersion is negative. In this case, the equation is called Kp2 equation. And they're unstable if dispersion is positive, in which case it is Kp1 equation. I have to emphasize that all these results were obtained for isotropic medium. In anisotropic medium, Kp equation takes this form. We have one additional term related to anisotropy. This is the additional term. If we linearize this equation, then it corresponds to the dispersion equation given by this expression. In isotropic medium, this quantity epsilon is 0. I also emphasize that in anisotropic medium, all coefficients of the equation depends on the direction of propagation. We can use a moving reference frame and reduce this equation to the standard form of Kp equation. In this equation, sigma squared equal to -1 corresponds to unstable solitons and Kp equation, and sigma equal to 1 corresponds to Kp2 equation when soliton is stable. So we can see that there is no difference. From this point of view, there is no difference between anisotropic and isotropic medium. However, Ostrovsky and Schreer also very long ago in the last century used methods of nonlinear geometrical optics, and they showed that solitons propagating in anisotropic medium are stable unless they propagate at small angles with respect to a critical direction, which is the direction where the phase velocity takes extremal value, or another definition where the phase and group velocities are parallel. This result contradicts to the previous result that stability is the same as isotropic medium. To resolve this contradiction, I have to emphasize that Kadamtsov and Petviashvili studied stability with respect to normal modes. And then I made a conjecture that actually Ostrovsky and Schreer studied stability with respect to bounded perturbations, although in their paper they never stated this explicitly. In this case, we have to distinguish between absolute and convective instabilities, and the situation becomes quite different. What is this distinction? This is the schematic picture of absolute instability. In this case, we have a bounded perturbation, but eventually perturbations grow exponentially in any fixed spatial position. On the other hand, in the second picture, we have convective instability, where perturbation also grows. However, at any fixed spatial position, it first grows exponentially, but then starts to decay and eventually tends to zero. Of course, the distinction between absolute and convective instabilities is frame dependent, because if we choose another reference frame moving together with the perturbation, then in this primed reference frame, the instability will be absolute. It is written. Now, in order to study absolute and convective instabilities, we use Briggs method, also dependent very long ago, to study stability of electron streams in plasmas. In accordance with this method, we need to obtain the initial, to solve the initial value problem for perturbed equation. So unperturbed solution to our equation is the soliton given by this expression. And now we linearize our equation about this unperturbed state and obtain this linear equation describing the evolution of the initial perturbation. Now we solve the initial value problem using Fourier and Laplace transform. This is Fourier transform, this is Laplace transform. We obtain, as a result, we obtain the following equation for double transforms quantity V, where V naught is Fourier transformed initial perturbation. Now we obtain complementary function. This is differential equation of the fourth order. We obtain complementary function given by this expression, and where kappa is one of the four roots of this quartic equation. We can use the complementary function to study the stability with respect to normal modes, the same as did Kadamtsev and Petryashvili. But they studied, they considered very long modes. We will now consider modes with arbitrary wave number. Normal mode is defined by this condition when the initial perturbation is zero. Using complementary function, we obtain the dispersion equation, and it is obvious from this equation that mode is stable when k is larger than omega than nu squared, and it is stable when k is smaller than stable when k larger than nu squared, and unstable when it is smaller than nu squared. In that case, the decrement is given by this expression, and it is obvious that it is takes maximum value. It is bounded. That's very important. This result was previously obtained by Zakharov and Kuznetsov. The maximum increment is given by this expression, and we see that all eigenmodes with k larger than nu squared are stable, so the increment is bounded, and our initial value problem is well posed. That's very important, because only for well posed problems we can study absolute and convective instabilities. Now we use the method of variation of arbitrary constants and obtain the solution to the initial value problem given by this expression, where both psi and d are entire functions of two complex variables, k and omega. So they are analytic in the whole complex plane k, complex plane k and complex plane omega. Now, the solution to the initial value problem is given by the inverse transform. This is the inverse Laplace transform, where function phi is defined by the inverse Fourier transform. Now we can study absolute and convective instabilities. Initially, we have to take the Bromwich integration contour above all singularities. This condition reduces to the condition that it should be above maximum value of increment. What we do now, we move our contour point by point down, like here. So the real part is fixed, real part of omega, and imaginary part is decreasing. If in this way we manage to move the whole contour slightly above the real axis, then our perturbation will damp and the instability will be absolute, will be convective. So it will be convective. We rewrite our dispersion equation in this form, cubic equation, and we can see that for any omega we have in general three solutions in complex plane. Now we are moving our contour down, and it can happen that at some point one of the roots will be on the k roots of our dispersion equation, will be on the real axis. Then we have a singularity in the integral defined the inverse Fourier transform. However, it's no problem because we can deform our k contour in such a way that we will that there will be no singularity on this deformed contour. We can do it every time unless there are two roots which arrive at different sides of our contour and merge at one point, and as a result they pinch our point. It is shown here. So one root comes from here, the second root comes from here. They pinch our contour and we can't move our contour further. If this happens when omega still has a positive imaginary part, then this means that our instability will be absolute. The perturbation will grow at fixed spatial position. But if it doesn't happen before we move the contour below the real axis, then instability will be convective. So the procedure is the following. We have to find all double solutions of our dispersion equation, so they satisfy dispersion equation, and also the first derivative with respect to k should be equal to 0. And then we have to, if there is such a double root with positive imaginary part of omega, then we have to show that the two roots which form one double root come from different sides of our k integration contour. Our analysis was carried out in a reference in a particular reference frame where our standard Kp equation was derived. You remember that we chose the moving reference frame. If since absolute and convective instabilities are frame dependent, we need to study it in different reference frame. To do this, reference frame moving with the velocity v in y direction, we simply have to substitute this expression for omega and then repeat our analysis. As a result, we obtain that instability is absolute only when v satisfies this condition. The most interesting is to study the stability in the reference frame where the medium is at rest at infinity. To do this, we take the reference frame moving with speed epsilon in y direction. Moving with speed minus epsilon in y direction. In the dimension less variables, this gives this expression for v, where t naught is an arbitrary constant with dimension of time, which we use to introduce dimensionless variables. This quantity will disappear in the final result. The solution is unstable. Soliton is unstable when upsilon satisfies this condition. Let us consider soliton propagating in the direction with wave number k. We introduce a critical direction with the unit vector e. Then we introduce the angle phi between the direction of soliton propagation and the critical direction. And we have this equation for phase velocity and this equation for group velocity. We can see that critical direction is defined by the condition that they are parallel, so it is phi is equal to 0, where our first derivative is equal to 0. Now, it is possible to derive these expressions for upsilon and for the quantity lambda, which is also stays in our KdV equation. And after that, the condition of absolute instability is given by this expression. We can write the expression for soliton in this form. And we can see from here that its amplitude is given by this expression and its width is given by quantity L. Now, we can introduce the dispersion length and we can rewrite the expression for L in this form. And then the instability criterion, absolute instability criterion, is given by this expression in the new form. We consider only weak small amplitude solitons where L is much larger than the dispersion direction. So dispersion length. So the phi, we can see from here that phi must be small, and we can rewrite our condition in this form. We can see that it is satisfied only for a very small values of, for small values of angle phi. So the absolute instability occurs only when propagation is at the small direction, at the small angle with respect to the critical direction. It is in complete agreement with the result previously obtained using completely different method by Ostrovsky and Schrier. Now I go to summary of my talk. First, we studied stability of KdV soliton using KP1 equation, where soliton is unstable with respect to normal modes. We used Fourier Laplace transform to solve the initial value problem for linearized KP1 equation, and the background state was the KdV soliton. Using this solution, we first reproduced the results concerning stability with respect to normal modes previously obtained by other authors. Then important property that we obtained that the soliton is unstable only for sufficiently long perturbations, so the growth rate is bounded, and the initial value problem is well posed. Then we used Briggs method to study absolute and convective instability, and the main result is that in the reference frame where the medium is at rest far from the soliton, instability is absolute only when the soliton propagates at a small angle with respect to the critical direction, which is defined by the direction where the phase and group velocity are parallel, which is in complete agreement with the previously obtained result by Ostrovsky and Schrier using methods of nonlinear geometrical optics.